Hey everyone. In this mini lecture, we're going to be discussing the idea of related rates. So, if we take a look at f prime of x, we define the derivative f prime of x. We define it as the rate of change of our function f of x with respect to x. Therefore, any problem or any question that talks about rates of change, we can reword the problem as a question about derivatives, right? When we calculate derivatives, we're calculating the rates of change. Sometimes you'll be working on some examples where more than one variable is involved, and then it's going to be your task to analyze and then create these relationships between the rates of change of these variables. So these types of problems are known as related rates problems. Let's step into some examples. So our first example says an airplane is flying directly away from you at 500 miles per hour at an altitude of 3 miles. So we want to know how fast is the airplane's distance from you increasing at the moment when the plane is flying over a point on the ground 4 miles from you. So our first step, if they don't give us a picture, then we need to draw a quick sketch or diagram. So here's our diagram. Because the plane is in level flight directly away from you, the rate at which x changes is the speed of the plane, and that's dx dt, equaling the 500 miles per hour. So the distance between you and the plane is s. It is that ds dt which is what we're trying to find out. We want to figure this out. And then by the Pythagorean theorem, we know that x squared plus 9 is equal to s squared. So taking the derivative with respect to the independent variable t, then we can obtain 2x, right? Using that chain rule, derivative of the outer, keeping the inner the same. And the derivative of x with respect to t is just that, dx dt. The derivative of any constant is 0. The derivative of s squared, let's say that's going to be 2s ds dt. We're using that chain rule again. The derivative of the outer, keeping the inner same, times the derivative of the inner. The derivative of s with respect to t is ds dt. So for us, we're looking and interested in the time at which x is equal to 4, as stated in the word problem. So we know that if we plug it in to there, we have 4 squared plus 9 is equal to s squared. So working out the algebra, we should get 16 plus 9 equals s squared, and then 25 equals s squared. So that gives us s is equal to 5. So now let's go ahead back to this equation right here that we have. So now plugging in 2 times x is 4, dx dt, well, that was given as 500 equals 2 times s. We just figured out s to be 5, and we're trying to figure out what ds dt is. So working this out algebraically, we get 4,000 is equal to 10 ds dt, dividing both sides by 10. Then we get ds dt is equal to 400 miles per hour. Our next problem says that water is poured into a conical container at the rate of 10 cubic centimeters per second. The cone points directly down and has a height of 30 centimeters and a base radius of 10 centimeters. The question says, how fast is the water level rising when the water is 4 centimeters deep at its deepest point? All right, let's take a look at how a diagram should appear. So our cone is pointing directly downward, and it has a height of 30 centimeters. And it also has a base radius of 10 centimeters. Again, so we want to figure out how fast is the water level rising when the water is 4 centimeters deep at its deepest point. And also we know that the water is poured into the container at a rate of 10 cubic centimeters per second. So the water forms a conical shape within the big cone. Its height and base, radius, and volume are all increasing, right, as the water is poured into the container. So this means that we actually have three things varying with time. The water level H, right, H, the height of the cone of the water, the radius R of the circular top surface of the water, the base radius of the cone of the water, and the volume of the water, V. So the volume of the cone is given by V is equal to pi R squared H divided by 3. So the independent variable here is time. So we know dV dt, and we want dH dt. So we have this third variable of R, whose rate we don't know, right? But the dimensions of the cone of the water must have the same proportions as the cone of the container, because if you take a look at them, if you were to draw a line straight up the middle, we could use the idea of similar triangles. So here we can say R over H is equal to 10 over 30. Right? R over H is equal to 10 over 30. H is listed it on this side, that height. So we can use similar triangles and create this proportion. R over H is equal to 10 over 30. So then we have 30R is equal to 10H, and then R is equal to 10H over 30, and then we'll say R is equal to H over 3. Right, the 10 over 30 becomes 1 over 3, which is just H over 3. All right, so now we can get rid of the R from that other equation that we had up here, right? So now we can have V is equal to pi, and instead of R, we can do H over 3 squared, right? And then we go ahead and say, okay, times H over 3. Okay, so doing a little bit of playing around with it, we'll get V is equal to, we can write it so it looks a little bit better. Have H over 3 squared, H, that's all over 3. Well, H over 3 squared is H squared over 9. And then we have pi next to it, as well as the other H. And that's divided by 3. Take it over here. It becomes pi H cubed over 9. And then it's divided by 3, so we can multiply it times 1/3. So we have pi h cubed over 27. All right, so v is equal to pi h cubed over 27. So now let's take the derivative of both sides, right? Take the derivative of both sides, and then plug in what we have. We have h is equal to 4, and dv dt we're told is 10. All right, so this over here to the right, what I've just written is the given information from the word problem. They're telling us that that 4 centimeters they gave us, and they gave us that 10 cubic centimeters per second. So we're going to plug that in and take the derivative of both sides. So on the left, the derivative of v, dv with respect to t, well, that's given as 10, so I can just write down 10. 10 is equal to, and now taking the derivative of the other side, the pi over 27, that's a constant. We can pull that out as a coefficient and then take the derivative of h to the third, right? So the derivative of h to the third will have that 3 come out using the power rule, and then the inner stays the same. So I'll leave the pi over 27 there, and then the inner stays the same, which is h. Well, h is just 4, right? So h is the 4, and you have to drop it down 1 as far as the exponent, right? Using the power rule, so 3 drops down to 2. Okay, and then the chain rule in this situation, because you're taking the derivative of h with respect to t, so it's dh dt. All right, so now we just do a little bit of math here. 10 is equal to 3 over 27. That's just going to give us 1 over 9. So I'll just write pi over 9 times the 16 dh dt. Okay, then lastly, dh dt, we can solve for that, get that by itself. What's going to happen here, we're going to have 90 over 16 pi. And this is in, let's see, they're using centimeters per second.